The question that I have is, could you describe the cross product between two vectors? As I mentioned before, the vector method involves the cross product between two vectors, so let's go ahead and talk about that first. Say we have two vectors A and B like shown in this picture. The angle between the two vectors is theta. We use this cross symbol to denote the cross product. So the cross product between vector A and vector B is vector C. So the important thing to note here is that the cross product is a vector. We know a vector has a magnitude and a direction, right? So the magnitude of the cross products between A and B is magnitude of A multiplied by magnitude of B times sine theta. We can figure out the direction of C using this right hand rule. So what are we doing here? Well, we hold the hand like this with the fingers going from vector A to vector B. Then the thumb tells you the direction of C. Let's compare the definitions of the cross product with the dot product that we learned earlier. If you recall, the dot product between two vectors A and B is given by this equation, right? So we usually write it like this: vector A dot vector B equals magnitude of A times magnitude of B times cosine theta, right? So here, in the case of the cross product, we have the sine theta in there. While the cross product is a vector, dot product is a scalar. So what is the use of the dot product? If you recall, we can find the projection of a vector, and we were interested in finding the projection of a force onto a arbitrary direction like this one right here, right? So let's say one vector is vector A, the other vector is a unit vector along the direction in which we want to find the projection of this vector, right? So let's just call that as little u. Then the dot product between the two is A dot u, which is magnitude of A times magnitude of u times cosine theta. But magnitude of u is 1 by definition, right? That's what we call a unit vector. And therefore, this is simply A cosine theta, which is the projection of this vector onto this vector, right? So that's one of the primary uses of the dot product. So what is the use of the cross product? Well, in this particular case, we're going to be using this to find the moment of a force. But we'll come to that in a second. But first, let's talk about how to find this. So we are given two vectors, vector A and vector B, in their component form, and we want to find the cross product between the two in its component form, like this. The question is, can we directly utilize the definition to find the cross product between the two vectors A and B? The answer is, in principle it's possible, but in practice it's difficult. Why? Because number one, we don't know this angle theta, right? All we know are these two vectors in their component form, like over here, right? But we don't know this angle, so we're going to have to first find that angle. So if we find that angle, then we can go ahead and find the magnitude by using this equation, because it's easy to find the magnitude of A, easy to find the magnitude of B. Now we have an angle theta, so we can use this equation to find the magnitude of the cross product C, right? But that's not the end of it, because we still have to find the direction, which is a challenging task. It turns out there's a systematic method that employs a determinant to find the cross product between A and B. And this is the equation. So what are we doing here? Well, this is the determinant of a 3 by 3 matrix. The first row of the matrix contains the unit vectors I, j, and k. The second row contains the components of the vector A, ax, ay, and az. The third row contains the components of the vector B, bx, by, bz. Now when you expand this determinant, you're going to find C in its component form. So what I'm showing on this slide is the first step of expanding the 3 by 3 determinant. The equation contained 3 terms, and how did I come up with these terms? Well, I start with this first term right here, I. So put that I over here, right? And then I draw a horizontal line and a vertical line through I, like shown over here. And these are the leftover elements, right? AY, AZ, BY, BZ. So they go in this 2 by 2 determinant. Then I go to the second element on the first row, j, and put the j over here, right? And then draw a horizontal line through j, vertical line through j, and take the leftover elements, which are ax, az, bx, bz, and put them in this 2 by 2 determinant. Now take the third element on the first row, k, and put that over here, right? And then do the same thing, draw a horizontal line through k, vertical line through k, take the leftover elements and put them in this 2 by 2 matrix, determinant. So that's the first aspect of that. The second aspect of that has to do with the signs. So you put a positive sign for the first element, first term, and then the second term has to be negative, third term has to be positive. Actually, if I had a 4 by 4, I'll keep on going like this, alternating the signs. Alright, so now we have reduced from a 3 by 3 determinant to an equation that contains 2 by 2 determinants, right? So now we have 3 of them. Now you expand these 2 by 2's using their very definition. So, for example, the determinant of this 2 by 2 will be ay times bz minus az times by. So you could use this road map to achieve this. So using the same methodology, expansion of this 2 by 2 determinant will be ax times bz minus az times bx, and this one will be ax times by minus ay times bx. So that's it. So we have C expressed in its component form. So this is the ith term, this is the jth term, this is the kth term. As an example, let's say this is A, this is B. We want to find the cross product between the two. So the first step is to construct this 3 by 3 determinant. So we put I, j, k on the first row and the components of the vector A on the second row, which are minus 100, 130 and 175, and put the components of the B vector on the third row, right, which are 4, 5 and 3. Next, you expand it in this equation that involves 2 by 2 determinants. Some people can do this in their head without making an error, but at this stage, until you get used to it, I suggest that you use a visual technique like this in order to come up with these numbers. Basically, you copy this 3 times, just like this, and then draw these lines, right? And then you know exactly the number that should go into each of these 3 2 by 2 determinants. Also note the signs. We have a plus here, minus here, and a plus here. Then you expand each of these 2 by 2's using this road map and simplify it. You also want to be careful in preserving the correct sign for each of these terms, especially when you have a negative sign with some of these terms like we have over here. For example, when we expand this, we get this times this minus this times this, right? So this already has a minus term in there, minus sign in there. So you want to keep that in there. So it'll be minus 100 times 3 minus 175 times 4. So this minus came from the fact that the formula for expanding the 2 by 2 includes a minus sign in there, right? And the same thing over here. So you got this minus 100, and therefore there is a minus sign in front of the first term because of that. So that's it. So we have the cross product C in its component form. Let me make a few important remarks before we proceed. First, we note that A cross B is not the same as B cross A. Actually, A cross B is exactly equal to minus of B cross A. Now, we know from the definition, magnitude of A cross B is simply magnitude of A times magnitude of B times sine theta, where theta is the angle between A and B, right? The magnitude of B cross A would be the magnitude of B times magnitude of A times sine theta, which is basically same as magnitude of A times magnitude of B times sine theta. So we end up with the same magnitude in both cases, and therefore the magnitude of A cross B is the same as the magnitude of B cross A, but not the direction. Direction is opposite, just like you see in these two pictures. Number 2, there are some interrelationship between the unit vectors I, j, k associated with the Cartesian coordinate system. For example, let's say we are interested in finding I cross j, right? So let's call that a C. So the magnitude of C would be the magnitude of I cross j, which is magnitude of I times magnitude of j times sine of the angle between I and j. The angle between I and j is 90 degrees, right? Because this is a Cartesian coordinate system, and therefore the angle between the axes are 90 degrees, and therefore the angle between I and j is 90 degrees, and the magnitude of I is 1 by definition, magnitude of j is 1, sine 90 is 1, and therefore the magnitude of C is simply 1. Now remember, we learned earlier that a vector can be represented in a number of different ways. A component form is one of those, right? And another way is that if you know the magnitude and the direction as a unit vector, right, then all we have to do is to take the magnitude and multiply that by the unit vector in that direction. Then we have the vector, right, represented in its component form, right? So using the same method, we can represent the cross product between I and j if we know the direction, right? So how do we know the direction? Well, we go back to this right-hand rule. The right-hand rule says that I cross j, the direction of I cross j is given by the thumb when we hold the fingers going from I to j, right? So I come back to this Cartesian system. This is I, this is j. So we hold the finger like this, going in the counterclockwise direction like that. Now thumb is going to be in the direction of the z-axis, right? So what is the unit vector along the z-axis? Little k, right? And therefore, the vector representing I cross j is the magnitude, which is 1, multiplied by the unit vector in that direction, which is k, or which is simply k. So in other words, I cross j equals k. What about I cross I? Well, by definition, I cross I would be the magnitude of I times the magnitude of I again, right, times sine of the angle between I and I. I and I would be 0, right? The angle between the same vectors, right, would be 0, and therefore this is 0. So you can see you can derive similar relationship between j cross k, k cross I, and so on. And these relationships come in handy in some equations when we try to simplify. Let's compare this relationship with those that we got from the dot product. Remember, I dot j equals magnitude of I times magnitude of j times cosine of the angle between the two vectors, which is 90 degrees, right? So, but cosine 90 is 0, and therefore I dot j is 0, whereas I cross j has a magnitude of 1. You see the difference between the two, right? And similarly, I dot I is magnitude of I times magnitude of I times cosine 0, but this time cosine 0 is 1, and therefore we end up with a number 1 for I dot I. So I dot I is 1, but I cross I is 0.